Is day 3 of definite integrals. So what you can do for questions 1 and 2 and 4, you can do those right now, and then when you're ready, I'll do the solution. So try this out first. All right, so for question 1, we are trying to approximate the area underneath the curve over 0 to 4, and we're going to use 4 subintervals. We're going to do for the left Riemann sum, the right Riemann sum, the midpoint, and the trapezoidal rule. Now for our left Riemann sum, right Riemann sum, and our midpoint, because we're using 4 subintervals and we're going from 0 to 4, that means the width of each subinterval is going to be 1. Because if you think about it, that means I'm going to create some sort of rectangle here, 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 and here, and that means we have a width of 1. So I'm just going to write this on the outside, and then we're going to multiply it by the sum of all the different y values for that interval. So the first one, we're going to use all the left points. So that's going to be the y value located at x equals 0, then x equals 1, the y value at x equals 2, and then x equals 3, and that's it. So I'm just going to write it like this because we are going to use a calculator to help us, to save us some time. I'm just going to say y of 0 plus y of 1, y of 2, and y of 3. So again, you can use your calculator for this because if you plug in x equals 0 into our y function, we're going to be left with 10. And then you're going to plug in 1 to get your y value and so on. So if you do this and simplify it, you should get 38. Now for the right Riemann sum, very similar, but in this case we're probably going to start at x equals 1 and find the y value there because we're looking at the interval between 0 and 1, and the right value is this one here. And then between 1 to 2, our right value is here, here, and here. So we're going to calculate y of 1, y of 2, y of 3, and y of 4. And this will give you 30. Now for our midpoint, we are looking at the middle of each of those sections. So between 0 and 1, our middle point is 0.5. Between 1 to 2, the middle point is 1.5. So we're going to calculate y of 0.5, y of 1.5, y of 2.5, and y of 3.5. This will be 35. And then lastly, the trapezoidal rule. So remember, the area of a trapezoid is 1/2 times base times h1 plus h2. So then we have 1/2. Our base is going to be 1. And then we'll sum up all of those h1s and h2s. So we're going to have 1 height at x equals 0. We're going to have 2 heights at x equals 1, all the way until 3. And then we'll just have 1 at x equals 4. So you can individually calculate this by plugging your x values into the original function and then multiplying by 2 for some of them and then adding it all together. So this will be 34. And this is the most accurate method. Now you're probably wondering why your LRAM is larger than your RRAM in this case. It's mainly because we have an upside down parabola. If we had a right side up parabola, and then it would be your usual LRAM is usually smaller than your RRAM. Okay, so for number 2, you can draw a picture to help you figure out the area underneath the curve. So I'm just going to do that. We're evaluating from -4 to -1, and then our line is at y equals pi over 2. So this is what we're trying to calculate. If you think about our length down here from -1 to -4, that is a distance of 3, and then our height is pi over 2. So this is 3 times pi over 2, length times width, which is 3 pi over 2. And then for this last one here, we can again draw a picture. This is a semicircle equation, but we're only going from 0 to 4. It's going to be a quarter of a circle, or half of a semicircle. This is the area we're trying to find. So we know that calculating the area of a circle is pi r squared, but we're only considering a quarter of it, so we're going to divide that by 4. So that'll be pi, our radius is 2, sorry, radius is 4. Then we have 16 pi divided by 4, and that's going to be 4 pi. For question 3, we had to look at the definition that we looked at yesterday, by definition, of those Riemann sums and how we took the limit of them. So this 1 over n is going to be your delta x. These are the sum of those f of ck's. Now, since your x, remember the ck is an x value. So your delta x in this case is 1 over n. And then your f of ck are the 1 over n's, 2 over n's, and 3 n's over n's. So if you can see a pattern that's happening. There is a squared being applied to the sum of these. So this has to do with your function f. So we know it needs a square. That eliminates this one here because it's not -2, power of -2. And also, in order to have a number in the front, like these ones, you need to have it at the very front of your limit. So we know it's also not b or e. Okay, so if your x value is a fraction, 1 over n, this 1 over n is also your x value. So I can technically replace this with an x here, if that would help you. So your function is actually x squared and not 1 over x. So that just leaves d for us. So again, your delta x is represented as a fraction, which means that all your x values in here are also fractions. And then you can replace that fraction with just an x to simplify things, which leaves you just with x squared, and that would be your function d. Okay, and then question 4 is just a review of the previous units that we have done. We're looking for C that satisfy the condition of the MVT of derivatives for f on the closed interval. Well, first thing we need to do is find the slope, m, between 1 to 3. So we need to calculate f of 3 and f of 0. This will be over, sorry, it's 1. This will be 3 minus 1. So that's coming from our interval. We can just put this into our calculator again to simplify some things. So we just need to plug in 3 into our f of x, so that'd be 3 cubed minus 7 times 3 plus 6, and that's going to be 12. If you put in x equals 1 into f of x, you're going to get back 0. So this is 12 divided by 2, which is 6. So in order for their mean value theorem derivative to be satisfied, that means that f prime of C is equal to f of b minus f of a over b minus a. That was their definition. Okay, so I already found this part here on the right-hand side of our equal sign. That is 6. And we can find f prime of c by taking the derivative of f of x. So this is going to be 3c squared by our power rule minus 7. And now we're going to solve for c. So if we do that, c is going to be plus or minus root 13 over 3. But we're only going to take the positive one because our interval is between 1 to 3. So our positive one is going to be root 13 over 3. And if you put this into the calculator, this will be about 2.082. So that is your value of c that will satisfy that condition. Okay, moving on to new things. We're going to look at rules of definite integrals. So there are 5 rules that you need to know. The order of integration. So if our intervals usually goes from smallest to largest, and we would read it off over here from A to B. Now, if you have a number on the bottom that's larger than the top, then you're basically flipping your integral, and it becomes negative. So the same thing what we can say is integral of a to b of f of x dx is the same thing as saying negative integral from b to a of f of x dx. So you're reversing the order of integration, you'll get the opposite answer. Rule number 2, if you have no width, so if we're going from a to a, then you're going to have no area, so then your integral is just going to be 0. It's like calculating the area of a rectangle with no width. You're just going to get 0. Constant multiples. So if you're left with a number k, so any constant number, you can always take it out of your integral. And it'll make your integral easier to integrate. The sum and difference. So if you have 2 functions inside of an integral, you can split the integral into 2 and then integrate them separately and then add them after. So this is one large integral, and through addition or subtraction, you can separate them into 2 integrals instead. And lastly, your additivity. So if you look at our bounds here, going from a to b and then b to c. This is equivalent to saying if we combined our bounds together, we can integrate from a to c instead, and we get the same thing. Okay, so we're going to apply that with a few examples on the next page. We're given 2 integrals, so f of x, the integral of f of x from 2 to 6, and the integral of g of x from 2 to 6. We know that the f of x one is 10, and the other one is going to be negative 2. So we're going to apply those 5 different rules to these examples. So this first one, we can, according to the sum and difference, we can separate them. So that's what we're going to do. So this is equivalent to the integral from 2 to 6 of f of x dx plus the integral from 2 to 6 of g of x dx. We know what this one is because it's given to us right here. So we know that the first integral is going to be 10, and the second integral is going to be negative 2. So then your final answer after simplifying is 8. Same thing for the next one. We can separate them into 2. So the integral from 2 to 6 of g of x dx minus the integral of 2 to 6 of f of x dx. So the integral of g of x from 2 to 6 is negative 2, and the other one is 10. Final answer is negative 12. We have a constant number in the front, so we can just pull it out of the integral and just evaluate our integral. And we know this is 10. I'm just going to multiply it by 3 now, which is 30. Sorry, this is just a typo here because it's the same one. And replace that with f of x dx, and then plus 2. So you're just going to integrate first. So the integral from 2 to 6 of f of x dx is 10. This is just a number outside of your integral, so we can just add it afterwards, and that's going to be 12. All right, so for example 2, we're getting a new set of integrals, but now we're still integrating f of x, but we're just given different bounds for the two. So we're going to go from 0 to 5, and then from 5 to 7. Now for the first one, for a, we can separate this into 0 to 5 of f of x dx, and then 5 to 7 of f of x dx. So this one here is just the combined bounds. Okay, which is 10 plus 3, and that's 13. For b, take a look at our bounds. They've been flipped. So this is going to be equal to negative 0 to 5 of f of x dx, which is negative, and this value here is 10, so negative 10. If your bounds are the same, so from 5 to 5, that means we have no width for the area, so that's just 0. And then lastly, we're going to pull this 3 out to the front, because that's just a constant number. And we know that the value of that integral is 10, so your final answer is 30. Okay, so the next thing we're going to look at is average value, and average value of a function in particular. So suppose we want to find the average temperature during a 24-hour period. How do we do something like that? So suppose we have an f of t that represents temperature, and the t is time. Okay, so then measure the temperature at equally spaced times of n. So T1, T2, T3, all the way to Tn. So if we want to find the average temperature, usually we just sum up all the temperatures and then divide by how many temperatures we have. But in this case, we're going to represent this in terms of f of t, because this represents the temperature. So I'm going to say f of T1 is the first one, f of T2 is the second temperature, and this can go on for n times. And then we would divide it by the number of temperatures we have, and we're just going to call that n. So this is your average temperature. All right. So the larger number of measurements, the more accurately this will reflect the average temperature. So if we have more of these different temperatures, you're going to have a better average temperature, a more accurate one. So we can also write this as a Riemann sum, because we are summing up quite a bit of terms. And we can note that the interval between the measurements will be delta t, because that's our change in time. And if we rearrange this, we're going to get n equals 24 over delta t. So we can substitute this n value into what we had in example 3. Okay, instead of writing n, I'm going to write 24 over delta t. Then in example 5, the last expression gives us an approximate average temperature as n approaches infinity. So that's from example 4, meaning that we are taking a lot of temperature readings. So this Riemann sum becomes a definite integral. You're going to write this definite integral that gives us the average temperature since nighttime. So I'm just going to rearrange this. So that's 1 over 24, which is the bottom part of, I'm just factoring out of our fraction, and this is left with the numerator. And then this delta t, because we're dividing by a fraction, this comes back up and multiplies with the numerator. So I'm just rearranging example 4. And according to this, from our notes from our last lesson, this is equal to, at least this portion is equal to the integral of 0 to 24 f of t dt. So that was the definition from the last lesson. And we had this 1 over 24 in the front. So that just stays there. So the last thing we're going to look at is, do you think that there is any point during the day that the temperature reading on the thermometer is the exact value of the average temperature? And that should be a yes, that eventually one of the readings will be the exact value of your average temperature. So the process that we just did to find the average temperature is used to find the average value of actually any function, just not that. So this is your definition of the average value. If f is integrable on a to b, its average value on a to b is given by 1 over b minus a, the integral of a to b of fx dx, or you could say the integral of a to b of fx dx over b minus a. So we're going to use this definition of the average value of the function on another example, a more geometric one. So we're going to graph x squared from 0 to 3 on the grid. So we'll point at 0, 0, 1, 1, 2, 4, and then 3, 9. Okay, our second step is to set up the definite integral to find the average value of y on 0 to 3. So I'm going to use the definition up here to do that for b. So b minus a, my b is 3, my a is 0. So we have 1 over 3 minus 0, and we're going from 0 to 3. Our f of x is x squared, then dx. And I'm going to simplify this a bit. Then it says use your calculator to evaluate the definite integral. So you can go ahead and do that. If you have your graphing calculator on you, then do the same method we used before to calculate the integral. You could also use an online calculator to help you for now if you want to use that. So if you plug this into your calculator, that's going to be 3. So we want to graph this value as a function on the grid to the right. And we want to know if this function ever actually equals this value. So that's our value over here. And it does seem to hit our graph eventually. We just don't know what the x value is. But we can solve for that. So 1 is x squared equal to 3. Well, we can square root both sides, so that's plus and minus root 3, but because we're going from 0 to 3, it has to be the positive value. So it's just going to be x equals root 3. That is when x squared is equal to 3. So the relationship between the area, the x-axis in the curve, and the area of the rectangle formed by our average value, well, they're the same. So the area underneath our average value here is the same as the area underneath the curve x squared from 0 to 3. So that means that the average value can give us the same value as the area underneath the curve given the interval. All right, So let's look at the mean value theorem for this now. So the mean value theorem says that if you're finding an area underneath the curve between some bound of a to b, then there is a c between that a to b, where it can use to form a rectangle that has the same area as the area underneath the curve. So the expression that we use to determine the area underneath the curve from a to b, that is your integration from a to b of f of x dx. And the area to find the shaded rectangle, well, we need to know this length, which is b minus a. And then we know this height is f of c. So that's b minus a times our height, which is f of c. So this value of f of c is just the average value of f. So we can rewrite this as, so we can multiply this b minus a times f of c, which is the area of the shaded rectangle, and this should be equal to the integral from a to b of f of x dx, which is the area underneath the curve. And we found that in our last example in D that they are the same. So I'm just going to rearrange this because we want to solve for the value of f of c. So f of c is the integral from a to b of f of x dx all over b minus a. And hello, that is right up here. You have that. So that means your mean value theorem is essentially the same as finding your average value. And that there's some number c that will do that. All right, so the mean value theorem for integrals then can be stated as what we kind of just found there. And then we can now apply this. So for example 9, we want to find the average value of the function y equals negative 3x squared minus 1. All right, so this is our interval. That will be your a, and that's going to be your b. So we have 1 minus 0. And then we're going to go from 0 to 1 of negative 3x squared minus 1 dx. And you can go ahead and just plug that into your calculator to figure that out. And that should be negative 5. And then for example 10, this is an old AP Calculus exam question. So we want to find the average rate of change of A of t, and we were given that. And this is the amount of grass clippings remaining in the bin. And A of t is in pounds and t is in days. So if you want to find the average rate, this is just going to be your y2 minus y1 over x2 minus x1. So in this case, we're finding a of 30 minus a of 0 over 30 minus 0. So you can do that calculation in your calculator there. It should be negative 0.197 pounds, because a of t is worth pounds, and then the bottom here is days, so pounds per day. Then in the next part, we're going to find a prime of 15, so we can evaluate this and even use our calculator to help us. So in your calculators, your screen is going to show something like this whenever you're trying to find the derivative, and then you're going to type your function in. And then it says evaluate at, in this case it's going to be 15. So if you do that on your calculator, it should be negative 0.164. So this is the amount of grass clippings in the bin that is decreasing. All right, and for C, we're going to find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the interval from 0 days to 30 days. So this is just the average value, which is 1 over 30 minus 0 from 0 to 30 our function a of t dt. And again, you can just put this in your calculator to calculate this, and you just plug in the function was given to you at the top here instead of this a of t, of course, and that would be 12.415. Then lastly, we want to do the linear approximation. So we're going to do this at t equals 30, and we want to predict the time at which there will be 0.5 pounds of grass clippings remaining in the bin. So this is your format for the linearization approximation. In this case, we're looking at a of 30 here, plus a prime of 30, that'll be our time minus 30. So a prime of 30, we can try to find this by, again, plugging this into our calculator to do that. So it's going to look very similar to b, except they're going to do x equals 30 instead of 15. A of 30, we can just plug 30 into our a of t in our calculator to figure out what that value is. And L of t is going to be 0.5 pounds, because that's what's given to us in the question. So if you calculate a of 30, you should get 0.782928. A prime of 30 is negative 0.055976. And then we have 0.5 pounds. Okay, so I'm just going to rearrange this and solve for t. So t, if you rearrange and solve, should be about 35.054 days. That is your final answer.